So, hello, ladies and gentlemen. A very good afternoon, and welcome to the College of Science Distinguished Speaker and Lee Kongqian Distinguished Professor Public Lecture. I'm Shivam from NTU School of Physical and Mathematical Sciences, and I'm honored to be the MC for today's public lecture. This public lecture is brought to you by the NTU College of Science and the Institute of Advanced Studies. We would like to thank our sponsors, the Lee Foundation and Ms. Alice Hung, founder of Pioneer Ventures. In view of the latest COVID guidelines, this event has been made possible in a hybrid mode. We are happy to welcome our audience here at the Nanyang Auditorium, and we also welcome those joining us on the live stream. To begin, I would like to invite Prof. Subra Suresh, NTU President, to deliver his welcome address. Prof. Suresh, please.
Good afternoon, everyone. Today's distinguished lecturer, Professor Didier Queloz, Your Excellency, Ms. Cara Owen, the British High Commissioner to Singapore, Your Excellency, Mr. Fabrice Fillier, Ambassador of Switzerland to Singapore, Ms. Alice Hung of Pioneer Ventures, distinguished guests, colleagues, students, those joining us online, ladies and gentlemen. I would like to convey my gratitude to Professor Didier Queloz for being here with us today to deliver the public lecture. Professor Queloz is the Jacksonian Professor of Natural Philosophy in the Cavendish Laboratory at Cambridge University and the Director of Leverhulme Center for Life in the Universe at that university. He's made outstanding contributions to the field of exoplanet science, which has mystified astronomers for decades and continues to fascinate us today. Until recently, our solar system provided us the only basis for our knowledge of planets and life in the universe. The question whether planets outside our own solar system really exist had been unanswered for centuries. In 1995, Professor Queloz provided an affirmative answer to this question. As part of his PhD at the University of Geneva in Switzerland, he and his then postdoctoral supervisor, Michel Mayor, made the first discovery of an exoplanet, a planet outside our solar system that orbits a sun-like star in our home galaxy, the Milky Way. This Nobel Prize-winning discovery started a revolution in astronomy and astrophysics, and forever changed the way we understand the universe and our place within it. Astronomers have since discovered some 5,000 exoplanets in the Milky Way, 5,000 strange new worlds, ranging from small rocky planets like the Earth to gas giants many times larger than the Jupiter with extreme climate variations. The immense new knowledge that we have found about these exoplanetary systems has stimulated fresh interest in the age-old question: is there life outside our planet Earth? Astronomers like Didier are now getting closer to finding exoplanets with Earth-like conditions and answering the fundamental question of life in the universe. For example, in a research initiative led by him, scientists have found the minimum conditions required to allow for the formation of life's chemical building blocks. In addition, his scientific contributions have enhanced the detection of exoplanet systems, and they have enabled scientists to gain a deeper understanding of how exoplanets form and evolve by comparing them with our own solar system. We now live in an extraordinary time where scientists can study exoplanets in increasingly greater detail and our ability to search for the chemical origin of life is much more advanced than even a few decades ago. Astronomers and scientists can now probe further into outer space than ever before as a result of multi-billion-dollar investments into space exploration, such as NASA's Mars 2020 expedition, and a new generation of ground-based space facilities conducting research on planets and life in the universe. All this progress has pushed the boundaries of human intellect and also research to a point where the quest for life in the universe is becoming achievable and understandable. My own scientific background is very removed from astronomy, but I had the good fortune of heading the US National Science Foundation about 10 years ago, during which time I probably spent more time with astronomers and astrophysicists than from any other group of scientists during the course of 3 years. As a result of this, vicariously, I gained understanding of the significance and impact of research in astrophysics. For example, during my time at the National Science Foundation, I probably signed the largest check ever that I could sign for ALMA, Atacama Large Millimeter Array Telescope Facility in Atacama in Chile in South America. We had the construction of what is now known as LIGO, which stands for Laser Interferometer Gravitational Wave Observatory, which is a collection of many countries, scientists from many countries, and primarily led by Caltech and MIT, and also facilities that has a 10-meter diameter telescope, which is the largest radio telescope ever built in the continent of Antarctica at the Amundsen Scott NSF South Pole Station. The impact of these scientific discoveries is unique and enormous. And our speaker today symbolizes the brilliance of the discoveries that are possible using those facilities that oftentimes don't start with the question, what is the translational value of this research? It's more of what is the fundamental value of the knowledge that it creates. It turns out that all these discoveries, including the ones that I mentioned in Chile, have led to a lot of translations of technologies that are used by industry all over the world, including the development of digitization tools, including advanced and sophisticated cameras that have been used for commercial applications, and many, many other areas. So in the conversation that we often have about basic research versus applied research, I want to make a comment that there are only two kinds of research: applied research and research that has not yet been applied. Professor Queloz talk today will provide us with new insights about the origins of life. To the students and young scientists among us, those joining us online, both here and those from different locations, I hope that today's lecture will excite and inspire you to learn more about the stars, the planets, and the wonders of the universe, and the wonders of life on Earth itself. In closing, I would like to thank the Lee Foundation, Pioneer Ventures, and Ms. Alice Hung for their strong support in making this public lecture event possible and a success. I also would like to thank the College of Science at NTU and the Institute of Advanced Studies for organizing this event. I wish all of you an inspiring and fruitful afternoon. Thank you.
Thank you, Prof. Suresh. Now, I would like to invite our guest of honor, Her Excellency Ms. Cara Owen, the British High Commissioner to Singapore, for her opening remarks. Ms. Owen, please.
particularly love that very groovy music that accompanied me to the stage. You don't get that every day. President Suresh of NTU, Provost, my dear friend and colleague, His Excellency Fabrice Fillier, Ambassador of Switzerland, Professor Didier, ladies and gentlemen, good afternoon. And good morning to those of you who may be joining us from a different time zone. I'm really delighted to be standing here and to be with so many of you in person, and also those of you joining virtually via the live stream. It is such a pleasure to be part of the welcome to this College of Science Distinguished Speaker and Li Kongqiang Distinguished Professor Public Lecture, hosted by the Institute of Advanced Studies at Nanyang Technological University. Thank you also to Professor Simon Redfern for inviting me to be part of the event. I'm particularly delighted to be here because since my first contact with NTU, I've been absolutely blown away by what an exciting institution it is, and I am absolutely full of admiration for the trajectory that NTU has been through in terms of zooming stellar-like through world rankings in a whole range of subjects. And NTU is also a really precious partner for us in the UK, for our universities with whom we are doing so much important research together. There are many, many, many personal academic connections, but also NTU is a fantastic partner for our companies who are working with them to solve the challenges that they see today. I'd also like to greet Miss Alice Hung, who is with us and who has helped make this lecture possible. As the President has already said, our distinguished speaker today, Professor Didier Queloz, Jacksonian Professor of Natural Philosophy in the Cavendish Laboratory at the University of Cambridge and part-time Professor of Physics at ETH in Zurich. In 2019, Professor Queloz received the Nobel Prize in Physics. And I think all of us know enough about Nobel Prizes to realize that if you get the one in physics, you've got the one at the very top of the rankings. And I'll tell you a little bit more about that in a moment. I'm so pleased that you're here, Professor Didier. For me, it's a signal of the fact that having been through 2 years where good friends and colleagues have worked together virtually, we are finally able, with the reopening of borders, to come together in person to do something that we all really love doing, sharing knowledge, sharing scientific excellence between our two countries. It's really refreshing to be back together. The UK's relationship with Singapore on academic and scientific issues is really long-standing, deep, and trusted. There are things that we can do with Singapore that would take us much longer to do with many other countries. We work together in in sectors such as economics and trade, education, science, innovation, technology. We are extremely close partners. Singapore has also been central to the University of Cambridge's international profile for many years. The Singaporeans who have chosen to have some of their education in the University of Cambridge, where Professor Didier is based, are an extremely precious resource for the university. Of course, Mr. Lee Kuan Yew, Singapore's first Prime Minister of independent Singapore, attended Cambridge, as did his son, our current Prime Minister, Lee Hsien Loong. There is a strong history of many talented students from Singapore studying in Cambridge, a tradition which I'm determined to make sure that continues. Before arriving here in Singapore, I made it my business to go around the UK, and everywhere I went, I asked to meet the Singapore students that were studying at the university there. And the group of Singapore students that I met studying in Cambridge absolutely blew me away with their quality, their interest, their engagement. In the academic year 2020 to 21, there were approximately 350 Singapore students at Cambridge, and that's the 6th highest within the international student population, and the 3rd highest in Asia after China and India, which is quite an extraordinary statistic when you think of the size of the feeder population. There are close to 3,000 Cambridge alumni here in Singapore, contributing right across economic sectors and in all aspects of society. In 2013, the University of Cambridge established its first research centre outside the UK. Remarkably, this was the first time that the University of Cambridge had employed people in another country, and it happened here in Singapore, a fact of which I'm really proud. The Centre for Advanced Research and Education in Singapore, also known as CARES, brings together researchers from the University of Cambridge, from NTU, this institution, and the National University of Singapore. They work with industry partners on problems relevant to both Singapore and the wider world. Programs initially focused on reducing Singapore's carbon footprint, thereby developing more sustainable processes for the world. Now, CARES also hosts collaborative projects in pharmaceutical industry processes, modelling for eco-industrial sites, and also the science of learning. But coming back to today's event, Professor Didier's Nobel Prize-winning work took place, it started during his PhD in the 1990s, when with his supervisor they announced the first discovery of a giant planet orbiting another star outside our solar system. As the president has already said, this created a real revolution in astronomy, kick-started the field of exoplanet research, and did so much to help us understand the origin of life. During the course of his career, Prof. Didier has developed astronomical equipment, created new observational approaches, and established new ways of collaborating to lead to enormous research advances. His leadership and participation in research programs has led to the detection of 100 new planets. I am truly excited by being here and being able to hear what he is about to tell us. I had the honor of being with Prof. Didier yesterday, and I hugely enjoyed the conversation. I know you're going to enjoy it too. I didn't tell him yesterday, but if you'd have asked me at 7 what I wanted to be, it wasn't to be a diplomat, because I'd never heard of them. It was, in fact, to be an astronaut. So being in the company of one of the foremost astrophysicists has been a kind of dream come true for me. And I would also like to pay real tribute to his generosity and his belief that he has to share passion for science, including with those of us that don't live life as scientists. Thank you again for inviting me to take part of this. And I really hope that you enjoy. I know you're going to enjoy the lecture. Get your questions ready. Thank you.
Thank you, Ms. Owen. Now let's get started with the public lecture. Before we invite the speaker on stage, please note that the question and answer session will take place after the talk via 2 modes. Audience who are present here can go to the standing mics at the center of the auditorium and ask their questions directly. All participants can also post their questions through Slido. Please scan the QR code shown on screen before we begin, and you can key in your questions as the lecture progresses. Our eminent speaker for today is Prof. Didier Queloz, who has laid the foundation of the exoplanet research. During his PhD, he, along with his supervisor, discovered a giant planet orbiting another star outside our solar system. He received the 2019 Nobel Prize in Physics for this discovery that kick-started research in the domain of exoplanets. Over the last 25 years, he has made significant contributions in the detection of over 100 planets with a goal to understand their formation and evolution. He is currently a Jacksonian professor of natural philosophy at Cambridge Cavendish Laboratory and also a professor of physics at ETH Zurich. His recent research interests focus on the detection of Earth-like planets, habitability of exoplanets, and life in the universe. The title of his talk today is The Exoplanet Revolution. So without further ado, let's welcome Prof. Queloz with a huge round of applause.
Well, thank you. Thank you for the very kind invitation, the kind words that I've heard just before. I must say I landed in Singapore a bit more than 50 hours ago, and I've just met amazing people. I've had amazing discussions, and I would like to thank you all of you for all these fantastic interactions. And I know most of you are here now in the audience, and thank you very much. In this lecture, I will try to convey my passion for science, and what I call, I think, a revolution going on in astrophysics. You know, science quite often surprises you, and sometimes the surprises are bigger than you would expect. And essentially, that's a bit what has happened 30 years ago here. By detecting planets orbiting other stars, we really opened a new chapter of the history of the science, and it's a bit like the long historical continuation from the time that we have set the Earth at the right location in the solar system, and we have just replaced the Earth in a more global context. So in this lecture, what I would try to explain to you is why it is a revolution, and why this new knowledge, why these many planets have changed the perspective we have on our own planet. So I will need to give you a little bit of introductions on how you make a planet to understand the consequences, what we have found. I will also try to push a little bit the boundaries here. And not only talking about the past and what we've learned, but the great expectations we have right now in this field. This field is changing many things. You will see it even changing the way we operate the science. And I have myself changed a lot the approach on this, and it was mentioned, I'm leading now a center, and I will try to bring you into this kind of dream ideas to look about life in the universe, and try to bring you into the process. How are we going to do that? You will see science is never an easy way, and we don't have clear answers, but I would like to bring it to you here, the pathway towards the discovery of life in the universe. This is why it's revolutions. So let's start with the beginning here. So where to begin the story? Well, let's begin where we have to begin the story, which is the solar system. This is the planet that we know very well. This is the planet for which we have plenty of picture. We have even more beautiful picture because we've sent probe around this planet. Well, I don't want to disappoint you here, but I want to tell you it's the only planet for a long time for which we're going to get such level of picture. There is not much hope that we'll get that level of information of any planet orbiting under the star. The reason is very simple, because you believe the solar system is quite big. Well, compared to the size of the distance between the stars, you're really on a small scale. So the next star is so far away that there is no hope, at least within certainly the next 50 to 100 years, to be able to reach at least barely some kind of nice picture, not even resembling to that. So this idea that we have the planet on the solar system as a test case has a profound impact, and had a profound impact in the way we understand more globally what is a planet. And practically one way to do that is to look a little more detail what we know about the planet. So I don't want to give you a lecture about planet. It will take way more than the purpose of this lecture. But I want to do something for you. I will just get a sneak in what is inside a planet. So what makes a planet interesting is the way it is built. And we know, for example, on Jupiter, that there is something in the middle of Jupiter, which is, let's say, like a core, something much more solid. The rest is essentially hydrogen, the same gas you have in the sun. And the fact you have this central core, which is similar in the case here of Neptune, has a profound implications on the way we understand the formation of the planet. So essentially, when you need to make a star, you just take a big cloud of gas and you collapse this cloud and you make the star. Eventually, you need to kickstart this collapse, but that's what you get. To make a planet is a complete different process, because once you have made the star, then you have a lot of stuff left over. It was mentioned before, the word ALMA, this fantastic series of radio telescope. I can't resist to show you what we can do with this kind of equipment that we're fortunate to have in astronomy, combining many different antennas, a telescope in the high plateau in Chile. We can detect that kind of picture. This is a real picture I'm showing you, which is a very young star in terms of astrophysics. So a young star for an astrophysicist is a star which has about 5 to 10 million years. To remember, our sun has more than 4.5 billion years. So this is what we are right now. It's kind of an adult phase for the sun. When you do that, you realize that you barely see the star here, because what you see is a thermal emission, something pretty cold, and you have all this material around. We call that a protoplanetary disk. Well, disk we all understand. This is a disk, clearly. Protoplanetary because it's before you make a planet, or at the stage you're making the planet. How do we know we're making planet here? Well, look at the shape of this disk. There is something strange here. It's a bit like a grooves into the disk. So this is kind of ripples. You see wave density you have that are created by something orbiting in the middle here, which is a planet. So this is a stage when you form a planet. So that stage is gluing together, piecing together what you have left over to make the core. And when you make the core, the gravity kicks over. You're reaching enough mass to attract everything around and to build the planet. So planet is built up by different phasing. You accrete the stuff bits by bits, a bit like a Lego game. You're building it on the top. And that's the way you form the planet. And that's the way we understand the planetary formation theories. So to go a bit more detail, I want to show you another kind of protoplanetary disk. In that case, using another fantastic machine that we all know very well, which is the Hubble Space Telescope. It's another stars, also within the same age, but the disk in that case is seen on the edge. You see the disk on the edge. There is two pictures here. The one on the top is the Hubble Space picture on the edge. The one on the bottom is the one produced by ALMA. It's a bit of a different picture, because in that case, we're sensitive to the gas. We're detecting a gas that we know very well, because it's one of the gas we're very worried about on the Earth is CO2 in that case. Let's start with the one on the top. The reason why I want to show you that is this famous disk is extremely thin, is extremely narrow. You see how narrow is the disk? Here there's a trick. We have just suppressed the star in the middle. The reason why I want to show you that is because the fact it is so thin means it is a very busy place. It's a very busy place. It means the particle, the stuff which is here, is bumping to each other. Because it's bumping to each other, it's gradually gluing to each other. It's building up. This is the reason why you're forming the core of the planet, because the physics of this structure is such that in one direction, you are limited by the motions, the rotation and the gravity of the system. But in the other one, is this direction, there is nothing. And actually, the particles are falling apart onto the disk. On the bottom, this is a very same picture with very same object in the very same scale. But in that case, what we do look at is the gas. In that one is the object, the small bits, the small grain of stones, anything, the pebbles, anything you can think about it. In the bottom, this is a gas. And here, if you're a physicist, you understand immediately what's going on. This is the fact that the gas has a different pattern than the solid particle, because the gas has pressure. There is something which is known as the hydrostatic equilibrium. That's what you see. This is the reason why you can go to the mountain and still breathe. There's less gas, but there is still some gas in the mountain. Well, if you just dump a stone out of the rocks, it will just fall down to the bottom. It will never stop. So the gas maintains some pressure here. So the gas is much more, I think, extended. You see in the vertical directions. But there is something fascinating on this picture, is the fact that there is no more gas here. You know, there is a kind of a cut. And it's not because ALMA is not sensitive. It's very, very sensitive. It's really nothing. There is no more gas. So why the gas is stopping here, while here the disk is continuing? The disk is much more extended. Because when you compute the temperature of the disk, you realize that at that point, the temperature is such that the CO2 becomes ice. Because you can imagine water, it would be exactly the same. So you have, if it's high, the temperature is high enough, it's a gas. If you cool it down, it becomes a solid. And if you understand that, you understand the formation theory of the planet. It means that here, all the gas you have has been changed, transformed into snow. If you want to make something simple. And this snow, because of the gravity, fold on the mid-plane, what you have here. And then you have a lot of particle here, a lot of material, which is just eating to each other. And this very specific region here, it's called the ice line. And this is a region where you very, very easily and rapidly build up a core. If you play with snow, you know what I mean. And you bring the snow together, you pack it, and you very rapidly make a big ball of snow. It's very easy to do. It's exactly what's going to happen. This very, very specific point about a typical distance when you get the snow and when they get a lot of stuff falling apart, define the formation mechanism of the giant planet. This is the reason why we believe that a planet like Jupiter has to be formed far away from the center. This is the reason why Jupiter is far away. And Saturn, this is why the big planets are far away. And this concept that I try to explain to you is the foundations of the planetary theory. And it has been confirmed by many different ways on the solar system. We know this is a valid concept. So for years, everybody was expecting all the planets to be similar to the solar system, because that's the way to make the big planets. And in the middle, you have not much left over, and then you form the small ones, like the small planet, like the Earth and Mars and Venus are closer to the sun, and the big giant planet are farther away. This is the concept that everybody had in mind before 95. Because what has happened in 95 is I use this new equipment to measure a star, actually the speed of the star, and what happened is the speed of the star was changing very rapidly and kind of oscillating with a periodicity about 4 days. And the only way to explain that is to have a planet like Jupiter orbiting that star. But that was just impossible, because the Jupiter is not supposed to be that close. 4 days mean extremely close, about 20 times closer than the orbit of the Earth. It was a complete contradiction with the planetary theory. Still, we were convinced that was a reality, and we made the announcements. And we announced a planet that was not supposed to exist, according to theory. So when you do that in physics, I can tell you it's bad. It's bad, and you better be really bloody sure what you're doing, because you're breaking apart the theory. And usually we don't like doing that, because the reason why there's a theory is a good reason usually. There has been plenty of explanations, and we have been battling for years to convince the community that was real. We were absolutely convinced it was real. It turns out that the situation was even worse than that. We realized there is even more planets that are not supposed to exist. And to show you a little bit the situation we are living right now is I have to go to a more complicated diagram, and just to give you the picture, when this is a summary of the 5,000 planets that we have detected, and using 3 parameters of this planet that we can kind of easily measure. One is the periodicity of the planet, of the orbit, on the horizontal axis in days. Here it's a logarithmic scale, so it's a scale that just gets bigger and bigger every time you move. And then this is the size of the planet in radius. This is 10 times the radius of the Earth, which is Jupiter. I put Jupiter here to help you. Jupiter will be there in this diagram. And this is a mass. The mass is 300 times the mass of the Earth. It's Earth mass, and that would be Jupiter as well here. So this is what we are right now. So there is not much planet been detected so far with the size and the mass of Jupiter. You see that. And we have this famous 51 peg planet-like, the world called hot Jupiter, the one we started detected. They are sitting over there. they have a size of about Jupiter, 10 times the size of the Earth, and short period, few days, here they are over there in mass. So this is kind of a blob of this object, and we have hundreds of them. We have a couple of planets that kind of could be compared to Jupiter, but if you look more carefully, you would realize that all the points you have here, most of them are clearly above Jupiter, and Jupiter is here. If you're just sitting here, you means you're 10 times more massive than Jupiter. So it means there is planet way more massive than Jupiter, and it was not really expected either. The big shock is it's not only there are planets like hot Jupiter, but there is this amazing number of other planets that are sitting between the size of the Earth and about Neptune's here, and the mass of the Earth, which would be here, one mass of the Earth, and then about Neptune mass, with a periodicity of few days to 50, 60 days. And that was not at all expected. This is a completely new population of planet that nobody had believed. So I used to call this diagram a gift of nature, because frankly, if when starting in 95, we would not have had this planet a bit that we don't understand, left with only these ones, today this field will not be at that level. And I would have never got the Nobel Prize, and there would be only a few planets, and not even sure, because who would do that? So the fact that there has been so many planets so different for the solar system, in a way, it's a gift, because it made the field much more alive. And every week there is new announcement, because all these planets are kind of easier to detect than the solar system. Now, to move a little bit further here, I said these planets are more easier to detect is because what I have to add to this diagram is the technical boundary conditions. What can we really detect? Well, this is about what we can detect. Anything on the left side of these two diagrams can be detected. Anything on the right side, impossible. For technical reason, for lack of time or number of objects, or just because the star is difficult to deal with and you cannot trust the star. So you really understand something quite crucial here. As of today, we have been looking at this part of the diagram, and in terms of size, because this is a transit technique, if you're familiar, I don't want to get into the detail, but this is a transit technique here being used. You would barely detect Jupiter, it's very unlikely, and you will not detect the Earth and Venus. Similarly here, this is using a technique to detect the mass, which is measurement of the speed of the star or change of the speed. You would also not be able to detect the Earth. So if you ask me the questions whether we know if Earth is common or not, the answer is I don't know. I know I can give you some idea about an Earth mass object and a size object, but not an Earth twin, really, because we have not been able to do it because it's difficult. Well, we're working on that. It's going to take more time. But still, from this, it has been a revolution, because I can push a little bit further, and then I can try to give you what is called the occurrence of each of these planets. So the idea of the occurrence is simple. You look at the sky, look at the star, and you ask the questions, how likely do I have to find a planet there? Or what is the chance to have a planet? Or what is the probability to have a planet? It's a complicated number to derive, because there's a lot of biases and elements, but together, this is about the number for the various populations that we have here, the three groups of planets we have. The hot Jupiter, the one that we found, is 1 to 5%. So the usual question, you've been lucky, you find the first planet, it was a piece of luck. I say, no, we just have enough objects. We observe more objects than the others. We have 120 objects in the sample. 1 to 5%, we had actually 2 of these objects out of all the whole series, so it's not a piece of luck. We just observe enough target, and statistically we had to detect it. It has to come. If you could do it, you would do it, and that's what has happened. The object like Jupiter, maybe 10 to 20%. It's a very interesting number. Depends how you set the limit here in terms of mass or distance. Because if you assume Jupiter is an archetype or proxy of a system like our own, you may end up with the conclusion, okay, possibly we have 10% of the star that have a planetary system like our own. But it's just extrapolating on the fact there is a Jupiter. But since we have been challenged by the formation theory, because this planet doesn't really fit the formation theory I told you about, it's not very sure. But the big stuff, and really it was a shock for the community, and it was really a true revolution. We have just found out that solar system is not that common. It's a bit like the story about putting the Earth at the right location. Remember, I told you, there has been a long process to make sure the Earth sits in the right location in the solar system. Well, we are pushing this. We're continuing this called the Copernican revolution here by answering not only how the sun fits into the solar system, but how the solar system is fitting amongst the many solar systems. And it's not that common, because the most common planet you would find in the universe, as soon as you point a telescope to detect this planet, is this kind of object. They are not this kind of object, 50 to 80%. It doesn't mean we are super rare, maybe 5-10%, but it means we're not common. And that was a big change. So how come could we have been so wrong with the theory I told you before? Well, because we kind of forgot a couple of additional elements, let's call it like that. It's a bit like if you want to predict the weather, but at some point you forgot that when you have a cloud, it may rain. And it's exactly what's happening here. Practically, as soon as you form a planet, the planet can move around. There is a lot of dynamic into the system, a lot of interactions that was completely overlooked into the system. And that's pretty clear right now that we tend to ask the reverse questions is, how could you stay where you are? Because solar system kind of never end up like that, and for good. Otherwise, we're not having this conversation, because it's unlikely there would be any life on Earth. The Earth would be rusted and very close to the star. So this is really the interesting bit right now, and I don't have an answer. But it's in that sense, we have completely twisted the game here. Now, with so much data, because all this, every point is a data, so it's a real measurement, and this is all science is being built, I can do a little bit of a trick here, because some of the stars, and you see there is blue and red dot, and red mean mass and blue mean transit, and there is some object which is blue on that side and red on the other side, which means they have both a mass and a size. So for me, it's great, because having both a mass and a size, I access to a new element, which is called the density or the bulk density of the planet, which is telling me a little bit what the planet is about, whether it's a dense planet or it's a very fluffy planet. When I do that, I'm ending with that kind of diagram. So in that case, this is a mass of the planet in terms of Earth mass. Remember, the Jupiter is here, and it's 300 times the mass of the Earth. At least this is a number you will remember at the end of the day, 300 times the mass of the Earth, right? And this is the size here. This is 10 times the size of the Earth. So we have all these points. There's a little bit of kind of wiggling here because these called error bars, which is the uncertainty, because it's a difficult parameter to combine here to show you it's not only a point, but a kind of a cloud around each of these points. And what I did here, and to help you to read this kind of diagram with a lot of points everywhere, I superimpose a series of density model. So if I know the structure of the planet, I can predict exactly where the planet will be on that diagram. And one planet I know very well is Jupiter. So that's why I added to this diagram the Jupiter density model that describes precisely how to describe the mass and the size of Jupiter. And this is this kind of line you have here in gray, the hatchet gray line. And you see Jupiter is there, Saturn is there, so they are very similar. They have a core, a lot of gas around. But there's something you realize when you reach the mass of Neptune here, it doesn't really predict very well. So the Jupiter and the Saturn model doesn't explain very well Neptune for good reason. That's why this planet is called an ice giant, because actually this planet has far less gas than these two there. It's quite often seen as a failed giant planet. So it is as if the planet had not enough time to capture all the gas around, and the gas went away before the planet had time to get it. And this is why the planet is denser. It's below this diagram. That's why for the similar mass, just more compact. Now, there's another model that I like very much because it seems to describe quite a lot of this planet, which we can think about the sci-fi planet. It's a planet that we qualify as ocean planet. It's made of water. So if you fill the planet with water, I mean, ocean planet, I mean serious ocean, not just a tiny 10 kilometers ocean. I'm talking about maybe 5,000 kilometers ocean. That's what I'm talking. It planet completely into like a water world. And you would be around that kind of structure here. So there's a lot of other planets that we have found that are clearly not like Neptune's, but seems to be like denser with a mixture of water world. We don't really know where they are. And we can keep going and we reach a density we know very well, which is the Earth-like density planet. And that Earth is here, is 1,1. And then depending how you play with the mass and the size, this is where Earth would be. So you realize right away that we do have detected planet that looks like the Earth in terms of density. So very certainly, a lot of these planets have some similarity with the Earth. The only caveat here is, I remember the diagram, they are on very short orbit. 1 day, 2 days, 10 days. It means that they're orbiting closer to the orbit of Mercury, extremely close. So it means they are extremely hot. It's an interesting planet because they're hot. Some of them are called lava worlds. You take the Earth, you move it to the sun, you will just melt it. At least the part facing the star, the day side, will be an ocean of lava. So sometimes I used to mention that sometimes the reality, the diversity of the planet is bigger than the best sci-fi author because you can create objects and you see there's so much diversity. That creates also a lot of confusions because you can have a mixture. You can pick a planet. Let's pick maybe 5 mass here, Earth mass. I can have a planet which is clearly like the Earth. I do have planet that seems to be denser. We call that iron planet. It's a planet which essentially you take only the core of the planet, the core what is inside the Earth, which is iron-based. It's also something that is possible. But you could also have the opposite. For the very same mass, you can have something very, very light and even extremely light planet. So we open a territory here that was completely unknown, and there is a diversity of the structure of the planet that nobody had predicted. So it gives a very interesting picture right now of the planetary diversity, which is a bit challenge, for all the field, and it's the main motivation why we're getting a lot of support and funding for new equipment, new development. One of the very famous and recent one being the James Webb Space Telescopes, because we're facing an extrinsic complexity right now to deal with what are all these other planets. So you have the one we know, which is the Earth and the ice giants, and then the Jupiter ones. But you see, there are something in between, and I just do some sketch because I'm not sure what it is. We have something in between here, which is maybe not sure if it's a big Neptune, so it's a small Jupiter, and we have all this possibility. You just make a big Earth, or you make the Earth but a lot of water. It's also a planet. You make a mini Neptune, so could you make something like maybe Jupiter that will be similar and smaller than Neptune? So that's why we are very creative, and we used to say it's super Earth and mini Neptunes and super Neptunes, all of this, because we don't really know what it is. Well, this is really where we are right now. But that's a tremendous stimulation right now to understand this. Now, why do we have so different kind of planet? Why there is only a very restricted set of planets in the solar system, and it's different from the complexity we have here? Well, my usual explanations is you can use the weather predictions. If you want to work for the weather predictions, if you're a physicist, you know very well, it's the Navier-Stokes equations, that's it. You can do whatever you like. This is the way you have to solve. It's not an easy to solve. It's an interesting mathematical problem. But Navier-Stokes equation drives the weather. So you know basically how it works. But how come it's so difficult to predict the weather? Because it happens that the equation of Navier-Stokes, depending on how you play the solutions, it's very easy to end up with a different outcome. And we know all that. We know the weather is difficult to predict after some time. Now, the reason why we have a limited vision of the diversity of the planet by looking at the solar system, it's as simple as imagine yourself living in Singapore. Do you have any idea, if you always stay there, do you have any idea that there are countries, like England, for example, that gets snow and rain and have a seasonal effect and all this? No, you don't, because you don't experience the same same basic element, while this is the same physics, but it's just the conditions are a bit different. And that's exactly what's going to happen here. So the planetary formations is in the same regime. We know roughly how it works, we know roughly the physics, but depending on the detail of it, you can end up with very, very different scenarios. And it gives this intrinsic diversity, which is extremely rich in terms of potential. Now, we're going to move a bit further and to ask yourself, how are we going to make progress into that? And that's an introduction, so a little bit to what is happening now and most of the activity and one of the reasons why we want to fly space mission and more, and we need bigger telescope. This is, for us, the perfect planet because it's a planet that is in transit. So it means we're just lucky to look at a system where, for a brief moment, the planet is going in front of the star, and because it goes in front, at some point the planet goes behind. These two specific moments are a bit magical for us. We call that transit. This is when we call the transit, and we call the eclipse because the planet disappears completely. They are very interesting moments because we can use this kind of system to learn something about the atmosphere of the planet. How does it work? Well, it's pretty simple. Well, let's imagine I'm in ISS as an astronaut, your dream, and I take a picture. I take a picture of the Earth with my camera, my cell phone. This is a visible picture, and the moon is in the back. Let's pretend the moon is a kind of sun, and you have then the transit, and you have something passing in front of it. Now, what I do see here is something which is always interesting to remind us is how thin is the atmosphere. You see something which is called the Rayleigh scattering, which is the reason why the sky is blue, and that's what you see here very well. It's about 10-15 kilometers. We're living on that planet thanks to the 10-15 kilometers. This is what is the alive part of the planet. As soon as you get above this distance, it's death, essentially. Now, if I take the very same picture, but I'm not using my cell phone that kind, but I'm using an infrared detector, one of the ones that the spy satellite are using, I will not see the atmosphere at all. I will see really the bottom. I will see the surface of the planet. Pay attention what is going to happen here at that level. When I do that, you see the planet looks a little bit smaller because that's a planet without the atmosphere. Now I can do a trick. I can select something I know I have on Earth, and thanks God we have it. It's called the ozone. It's protecting us against the UV, the deadly UV that would essentially sterilize every life on Earth if you don't have it. This layer is extremely high. It's about 50 kilometers high. And I will select my wavelength to a specific regime when I'm sensitive to the ozone band. And what I will get, and pay attention, it's the same location to what's going on here. What I will get is this. The planet is much bigger. So this is a trick we're using. When you measure the size of the planet, because that's exactly the transit, you get different size depending on the wavelength you're looking at. And essentially what you're doing is you're probing like an X-ray through the atmosphere. Some of the wavelengths, they will go straight, others they will hit something and they will not go straight and they will make the planet bigger. And that by this technique that we can reverse the understanding of the atmosphere. And that's how, you may have heard, we have detected water. We have detected water under the planet. And again, people say, water is a magic. Well, water is the most basic molecules you find in the universe for the simple reason is made of hydrogen, which is the basic atom produced by the Big Bang, and is used oxygen, which is one of the key atoms being produced by the stars. There is a mechanism it's called the CNO cycling, which is producing oxygen. So oxygen and hydrogen together makes water. You point any radio telescope into a molecular cloud, you will find plenty of water. So it's nothing magic, it's not a surprise, but it's nice to understand that. Of course, we detect much more than the water, and you can imagine all the gas. So this is one trick we're using. But we can do even better than that. And to understand, I have to get you a little bit of an insight as an astronomer, what I'm doing, what is my day life fun, is to take a telescope, whatever wavelength you like, and to record the transit and continue measuring the transit along the time. I happen to fly a satellite called Queloz right now, which is a space mission, European space mission, and this is what we're doing. And then what you would do, you record the flux, you record the amount of energy coming from the stars, and there is a moment where you will have a bit less light, which is the transit, because the planet is going in front, would be that moment. But what I'm very interested about is the other moment, when the planet is behind, what we call the eclipse. Why? So let's zoom in here. We're zooming in, because when you think at that very moment here, when the planet is behind, that's the only moment when I'm sure I only see the star. I don't see anything from the planet. The planet is behind. So it's a clear definition of where is the star. When you think about that, when you do what's called a Gedenk experiment here, and you think about that, you realize that these two specific moments define the flux from the star, the amount of energy or light that the star is giving you to the telescope. But actually, you record way more. You're recording all that as well. So anything extra here, anything in excess, comes from the planet. This is how I can detect the night side, it's darker, there's less flux here, from the day side. And I can use that to compute the temperature of the planet. And again, blending with different color, I can have a feeling whether there are clouds and fogs and anything like that into the planet. So this is how we're doing it. This is how we're doing it. This is what we are doing. This is what we are about to do with the famous James Webb Space Telescopes, is to approach the understanding of the atmosphere of a planet. Now, there's another exciting topic now I have to introduce. We have plenty of planets very close to the star, that you understand. But you understood also that we have also planets similar mass and similar size to the Earth, but very close to the star. Most of them, the star, like the sun, will just beam them too much. They will be extremely hot. They will be lava world, which is interesting by itself. But some of these stars are not exactly like the sun. They're much more smaller. And when you have a smaller star, the star is shining, it's much more dim, doesn't shine the same, so the temperature of the star decreases. So essentially, you can stay much closer to the star without being burned, without being completely a lava world. And there's a very extreme system that I was part of discovery with my colleagues of Belgium, which is the TRAPPIST system. The TRAPPIST system is a system of 7 planets. And if you scale it to the solar system here, the system will be very close. It will be exactly like that. I told you most of the systems we have found are extremely close, and this is one of them. But what makes TRAPPIST interesting is the star is very, very different. It's called a late M star. It's a very cold star. Our sun has 5,700 degrees at the surface. That star has less than 3,000 degrees. It means you can go much closer. And when you compute how close you can get, you realize that the system, which is exactly here, there is a nice temperature for 3 of the planets. This is what we call the habitable zone. It's just a theoretical area where if you imagine an atmosphere similar to the Earth, which is an assumption, it's not proven in that case, then the water on this atmosphere will be liquid. So formally, it's the definition that defines the minimum conditions. It's only the minimum conditions to have liquid water. It doesn't mean there is liquid water, but it means if you have it, it's still liquid. And that is possibilities that the 3 of these planets that are similar to the Earth have a good condition for life. So this is today, that discovery was in 1617. This system, there is at least 2 weeks of observation plan on the James Webb Space Telescope to get the atmosphere of this planet. And people were super excited to find out whether there are water. Water would be really tremendous because the fact that you have or don't have water would give you already a clue. And the reason why I mentioned water, you may have read recently a controversy about Venus. Venus, you know, is a deadly world right now. It's very hot. It's a greenhouse, terminal greenhouse effect. And Venus is not very different from the Earth. It's same mass, same radius, a bit closer, but it's not dramatically closer to the sun. So the big question is why Venus is like that. The big reason why Venus is like that, because they don't have plate tectonic on Venus, recycling the CO2. And then there's too much CO2, and you end up with a terminal situations, and that's it. And why there is no plate tectonics on Venus and there are plate tectonics on Earth? Well, a possibility here is because one had water and the other one had no water. You need water. Water is the kind of the oily mechanism to make it work. Without water, there is no plate tectonics working at all. Maybe Venus had much less water, or maybe lost the water, or missing the water, and it has been recently acclaimed that this is really one of the reasons why. So this is why the origin of the water is really fascinating, because it's one of the key starting points to imagine the possibility of plate tectonics. And we need some recycling of the CO2, otherwise the planet will end up like Venus. Maybe the majority of the planet, like the Earth, will be like Venus, or maybe not. I don't really know. But we are going to find out, because we have the technology, we have the tools, and there will be further improvements or further. If we miss it because this telescope is too small, the James Webb, I'm talking about James Webb, we will build the next generation later on, and we have a telescope on the moon, and it's going to happen anyway. There is no limit of physics yet to breaking to do that. Now, I'm talking about life here. I'm talking about water. So the big challenge that we're facing right now is, if you really want to make progress into that, we have to define what we need to talk about. What is really is the key here. And I must say, I had an experience. I was lucky because I met one colleague in Cambridge through a program funded by Simons Foundations. And this colleague is John Sutherland, and he is a biochemist. And he really, in the discussion we have had, he mentioned to me that progress has been done on the origin of life, substantial progress, with a model, a chemical modeling, which is a big change from the kind of idea that was a couple of years ago. And this model is reflecting very likely the possibility of what looks like a planet at the early stage. Which you take a planet like the Earth, you have water, you have the plate tectonics, means you have volcanoes, so you produce a lot of SO2, SO3, and you have a lot of cometary falling. The early stage of the solar system, there's a lot of comet falling, and on the comet you find very easily HCN. HCN is a cyanuric acid, it's a deadly gas. If they would put a little bit here, we would all die. So it's not something that you connect to life, but apparently at the beginning of life, it may have played a key role into the early chemistry here. And what John mentioned to me is you don't need a fancy atmosphere, kind of regular atmosphere seen from the planet perspective, which to me is fine, because this is something I can test as an astronomer. But he mentioned to me you need UV flux to produce the energy to make the chemistry work. If you're a chemist, if you know chemistry, you know to make chemistry happening. And even if you don't know chemistry, if you do cooking, you know that you have to do something to make the cooking working. You have to warm it, you have to shake it, or in that case, you have to beam it with light. In that case, there is no ozone at that stage, so it's a UV light. It's very energetic. And what has happened, and it was mentioned early on, that we produce a couple of papers that demonstrate that this mechanism can produce the key ingredients for life, and it's actually there is a whole mechanism that is related here. There's just organic chemistry, which is producing the key ingredients of life, which is the amino acids. You need to produce the nucleotides. You need to produce how do you bring the cells, all these elements together. And the chemistry seems to produce the basic element about this in the right proportions, what we expect. The fact that it's 20 amino acids was a bit puzzle, but apparently it followed naturally this kind of mechanism. And there's a couple of papers if you want to go through that. And that completely has changed the game, because it means if the origin of life is on the surface of the planet, which is the claim here, but it doesn't need to be deep in the oceans, and there is predictions that you need some ingredient, this and that, we can test it. We're going to test that. We're going to look whether there is water. We're going to look whether we have a trace of HCN. We're going to look whether there is SO2, SO3, because this is, you can detect it. It creates molecules that can be detected remotely, and you can find out the proportion you have, and you can find out whether there is some interesting chemistry going on. And that has been a twist into this global idea that looking for life, there is a hope that we may make progress by understanding better what's going on the planet by looking at the atmosphere. But there is a big missing ingredient here. If you really want to understand that, you have to understand the planet. And that was the last bit that is a bit more recent. We've started to engage quite a lot with geophysicists on that program, and they help us to understand, and they're very interested about the program, and we produce this nice diagram here to show you a bit what it is about. This is the Earth. This is the history of the Earth in 4 different phases. The early phase, it starts here. It's the astronomy phases when you build the Earth. This is my bit. I can produce this element there. I can produce the ingredients, and this is the starting point because they define the chemistry of the planet. You get what you get when you form the planet. That's it. And we know Mercury is different from Venus, from Earth, from Mars, and this is what we could do. We could get an idea what it is here. Now, the planet evolved. There is a lot of info. There is a cooling down. There is a sinking of the heavy elements. So the planet evolves here and change. There is a change, and we have this very exciting moment here when we call magma ocean planet. Well, magma ocean planet is something we like very much because we do have plenty of magma ocean planet today that we observe with our telescope. They will stay like that forever because actually they are magma ocean planet because they are so close to the sun. But then we can study indirectly the situation on Earth by looking at these many different planets. And then you start understanding something really crucial here. You can study life the way we know it on Earth. That's it right now. There is no other way to do that. You can explore life on the solar system, on Mars, on Venus, maybe the icy moon of some giant planet on the solar system. It's expensive, but it will happen because we know to do that. We know to make probes, space equipment that will go there. But it's still limited. Once you've done Mercury, Venus, Mars, and you go to Europa, Callisto, and then that's it. You're done. You have an infinite number of stars, essentially. And you know there is plenty of planets. So technically, we have a lot of planets that we can look at, but we will never look as good as we're looking at the one from the solar system. So it provides this kind of diversity, and we can use it this carefully. And that phase, today we can detect and observe it, and there's a couple of systems that will be observed with the James Webb Space Telescope, indeed, and being observed by other equipment to understand where they are. Now, after the planet cools down and you start to see something we know very well, you should expect to see water, CO2 and SO2. What I mentioned is the volcanic activity. This we can detect. There are systems. The planet is not completely hot, but we do have systems called warmish that we can detect, and that is something we will be doing. So this 3 element here, we can do it in astronomy. The more challenging bit is the last one, because there is a point where you start developing life on Earth. And quite early on, actually, after the first billion years of existence of Earth, you have life already. And then you start to change the atmosphere. So small planets are known to evolve and to change, have the atmosphere changing. And that's the key, and that will require new equipments. We're not going to do that with the Webb, but we're going to pave the way to the Webb to the next generation of scientists that will build up an even bigger telescopes. And we start probing of this system. But we're going to find these planets, I can tell you, because we're working very hard right now with an international consortium to find this planet. And then there's 2 options. Maybe you don't make life. You end up with a no-life planet. That's it. Or maybe you make life. How different will be the planet? What is exactly the structure of the atmosphere? I don't really know, but I know we're going to proceed. And that's what I want to show you here too. I'm close to the end of this conferences, is these different phases. The early phase here, that one and that one have a different signature. So if I can measure the atmosphere compositions, even without understanding everything, I will see a very different planet. And you see 3 stages of the Earth: the archean Earth, which is that stage; the Proterozoic Earth is when you have life already, but that's not at the time when there's enough life to modify dramatically the atmosphere. And then there is a modern Earth, which is right now. And maybe if we keep doing that way, we'll keep changing the atmosphere because the industrial production is changing completely the nature of the atmosphere. You can imagine we're going to detect maybe some gas that we may be able to identify as being a productions of a very highly developed life on the planet. And I do much believe, according to what I do see on Earth, the fact we have an impact and we're changing, we're terraforming the Earth right now, and that's completely is happening. And whatever we do, we are changing it. Even if you stabilize the climate, we'll keep changing it because the development of the structure of the Earth, we've completely changed the Earth. These traces that may be detected, and I do believe way more to that kind of detections than trying to listen for radio ET that some other people are doing here. So this is the way to go. So in terms of astronomy, we're going to replicate that. Of course, it will be complicated, but we have a proxy. We have a couple of proxies. And I was mentioning right now the planet of the solar system. This is one you know very well, it's Mars. We have the robots right now. So why are we exciting on Mars? Why is it so exciting to be on Mars? Because it's a specific point in time of the solar system, and a specific point in time when we do believe there has been life. The landing site of the robot is here. It's a Jezero cratera. You don't need to be a geophysicist to recognize here. This is the result of a river. It's a delta, actually, you see here. This is the reason why it has been picked. And the robot is going to go from here, going up and going up and going up. It's going to just get sample and sample along the way. The idea is to get the chemistry that has happened in that region. And why are we so excited? Because we know for sure right now that if I go back in time, after 1 billion years, when the system has been formed, the solar system, this is how it looked like. So I know it was like that. And it's exactly what I was looking for, the origin of life on Earth. But this trace on the origin of life on Earth is gone because of the plate tectonic. Everything has been recycled, and it's gone, and it's completely erased. So we have not a single trace of that moment on Earth. But there is a belief that Mars is kind of similar, evolved similarly, which is not 100% sure. So if there has been life on Earth, why not on Mars as well at that very same moment? Because the condition was not very different. So maybe there is some traces. When I say traces, is traces through the chemistry. The chemistry, life produce impact. It's changing the chemistry. You don't get the same chemistry with life that without life. And if you can bring back sample, the degree of analysis we have, the level of the detail we're going to get, looking for isotopes and some effect, will be so amazing. So we do believe we should be able to say something. We know already that that was the case because it has been demonstrated that the bottom of these places was full of water because the water is changing very easily some chemistry on the rocks, and that has been detected. And that is what we're going to do. So that will give us a very interesting already clue whether some assumption we're making are correct. And the next stage will be to move that to the other stars and to the other planet. Well, how are we going to do? We're going to ask a specific questions. So if you look at the evolution on Earth, you can reflect that with the evolution of the major gas you had. And I want to pick some of them. Oxygen is a very easy one. You have essentially no oxygen on Earth, and then you have these big oxygenations related to life, and then there's a bit uncertainty, and then another bump here that is changing the signal. You have the carbon dioxide that was very high at the beginning and completely dropped. That was a very dramatic event on Earth at that point, because the carbon dioxide maintained Earth in a greenhouse effect, very warm. At that time, the Earth became extremely cold, and it is believed that everything kind of stopped on Earth, and the Earth became a kind of ice ball at that time because you don't have anything to keep the heat standing on Earth. So the rise of oxygen and decrease of carbon dioxide may have been the end of it, maybe the end of life. The concept of life, once you have it, doesn't mean you will keep it always. So it's also something we're going to test. I think it's not only about starting life. Maybe it's easy to start life everywhere, but are you going to keep going on? Are you going to keep the planet alive? Do you need to evolve then every time? We don't really know that. It doesn't mean that the pathway we have had is the same elsewhere. And that is something that we should be able to test by looking at many different planets. So the trick here, you can have all these assumptions together and you test some of the gas, and then you have some assumptions. So you know that if you have had, for example, the massive volcanic activities, so this is going to leave some traces, and we're going to use molecules into the atmosphere. And that is this diagram that is extracted from a report on the future generation of space telescope. This development has been essentially led by NASA. It's a LUVO project here. And they have identified It's an international project, and they have identified the origin of some gas, and the idea is anything here will be tracing something about the history of the planet. It's a bit of the DNA story. Then now we can, by looking at the DNA, we know exactly what it means. Well, not exactly, but we have a good understanding. That's enough. So the idea is it's a very early stage, but it's exactly the same. To use these kind of molecules you have in the atmosphere to rebuild the story of such a system. And that is coming. It's not for tomorrow, but that's just for the day after tomorrow, whatever scale you want to use here. And I usually take a very optimistic stand here, and I say, I'm pretty sure in 30 years, we will have something here. Something related to this approach is fascinating because you already understand something, which is called the uncertainty or probability here. I don't think we will have a black and white answer. It will be a more likely answer, or the high statistical elements. It will be about possibilities, but there is this understanding when you add more and more, you add more planets, and we will, because we have almost an infinite number of planets we can look at, then there will be a growth of knowledge. And that growth of knowledge will tell you more and more about the questions of life or likelihood of life in the universe. So you already understand a bit all the bits. Now, the challenge when I started working with John Sutherland on that project was for me to understand what John was doing, and for John to understand what I was doing, because I brought some equipment in his lab. We had a lot of fun combining our project together. And I realized that the challenge of that new discipline, because it is a new discipline. It's just a new discipline. It's a question of life, dealing at the origin of life, question of life in the universe. It's also the intrinsic build-up, which is intrinsically multidisciplinary. So you need to combine all these different fields together. And I was the strong motivations behind setting up a lot of my colleagues together from chemistry, biochemistry, geophysics, math department, physics department, astronomy department, together trying to build up a kind of process how to operate. And we've proposed a center in Cambridge. It's called Leverhulme Center for Life Universe. And we won it. We've been selected. Now we are about to start the center. The center will be launched in June. And the fact we've done that, you know, when you're a good idea, you're never the only one. Actually, I've learned recently that Chicago is developing something similar, led by Jack Szostak, another Nobel Prize, but more on the biochemistry, that kind. And I learned also the Carnegie is interesting to move in these directions, combining the planetology, they're very strong into the planetology. And recently, I moved to Zurich, ETH, for this very reason, because my colleague at ETH, the earth scientist, biologist, biochemist, chemist, and astronomers and physicists had exactly the same idea. And I started to realize, and we're all talking together, all this different community, that together we're going to build a kind of new knowledge here, and we're trying to build this new kind of approach that will eventually get an answer to, I think, one of the most exciting and mysterious questions about, essentially, are we alone in the universe? Thank you very much.
Didier, go. Thank you, Prof. Queloz, for sharing your experience and interesting discoveries with us today. Now let's move to the question and answer session. Audience present here can go to the standing mics at the center of the auditorium and ask their questions directly. All participants can also post their questions through Slido, so please scan the QR code on the screen. With this, I would like to invite Professor Simon Redfern, Dean, College of Science, to join Professor Queloz on stage and moderate the Q&A session.
Well, thank you, and thank you, Didier, for that fascinating talk.
My pleasure. No, that's the most difficult part.
I'm sure it's raised a huge number of questions in people's minds. One of the first, maybe I'll kick off with a question that was occurred to me for your early discovery of these very large planets close in to stars. You mentioned the difficulty in thinking about other scenarios, other environments. Does this mean that there are planets out there that are very like England? They have 4 seasons in 1 week. You know, is this?
That's exactly what it is. Exactly. With a slight difference is the planet is so close to the star that there is what's called a synchronization, like for the moon. Remember, the moon, you only see one face of the moon because the moon rotates at the same period that the orbit of the moon. Is called a synchronized system. So, and this happens when you're very close and the ratio of the mass are not enough for maintaining the difference of rotation. So we do believe that they are synchronized. So it means there is a permanent day side and a permanent night side on this planet. So it's a bit of a different scenario with huge wind between the two, you can imagine, because of the heat and the cold of the space on the other side. So it's really not the kind of planet you want to go.
There's a couple of questions that have come in, and I think they link into your first discovery, you know, that you made during your PhD. That, as you explained, that was driven by technological developments, developing detectors and understanding the data that those detectors were able to provide. There's a question here from Simyu Yang from the Asian School of the Environment, another one that's come in anonymously, which is the impact that the James Webb telescope will have. So the current technology, you've talked about future hopes for technologies, and we've seen James Webb unfolding fabulously recently.
Well, James Webb is a fantastic toy for us because it was really, originally it was not designed at all to do planetary sciences. James Webb, it's a telescope which is built and designed to look at the faintest possible stars in the galaxy in the universe. And space development of that size, of that scale, of that complexity takes a long time. So essentially the design of the Webb started and was defined before we started detecting the first planet. But it was pretty clear when we started picking up planet that the Webb could play a role, and they did something which is very rare in this space business. They changed the design along the way. Usually you never do that because it creates a lot of problems, because the simple problem the Webb had, most of the planets we've detected are orbiting bright stars. And the Webb could not observe bright stars at all. It was not designed. It was observed to observe very faint objects. So they had to implement a couple of tricks. And to the big surprise of the NASA community, but not to us, when we went to the competition to win the time, 30% of the Webb time has been allocated right now to program related to planetary science. So it was a big surprise because people believe that, well, there would be just a niche project. So really the planetary business has grown tremendously. It is such that the next generation of space equipment, similar, would be essentially designed to do atmospheric studies and detecting molecules into planet. And I was mentioning LUVOIR, which is the kind of machinery or similar machinery we're all dreaming about.
Mm-hmm. Very good. I'm going to switch track a little bit. There's a couple of questions that have come in, and the audience is very diverse. It's a kind of fascinating question from Yap Peng Huat Eric, which is the impact of science fiction on public awareness and hypotheses in exobiology. Is this a useful or a damaging thing? And I say this having, during lockdown, read The Three-Body Problem myself. So
Well, I myself, I read some science fiction, so I like it. I think it's good stuff to do. Science fiction is dealing with all the possibilities. This is the way science fiction works. My take on that is the reality tend to be even better than the science fiction, so it'd be more creative. I think one of the usual challenge on them when I talk, I've been invited to a sci-fi festival, and I used to just joke at them. I say, well, you never predicted hot Jupiters. So it's difficult. I mean, science fiction is using the present situation, present knowledge to project into the future. But when you have something you don't even know it exists, it's very difficult. So I tend to say that the reality is even more exciting than science fictions. But I like science fiction, so I have no problem. So I don't think there is anything bad or wrong. I think it comes in addition. It's a very interesting literature, and if it brings some people to science, well, I'm very happy. So it's good for science fiction.
Okay. another question relating to the sort of bias that we all have based on our own experience and understanding.
Yeah.
Was in your talk, you've talked about the search for the origins of life and for life in exoplanets. And this is a question that I think often comes up. The assumption is that life is carbon-based.
Yeah.
And is that, how reliable an assumption do you feel that is?
Well, there is a lot of assumption about life, but there is some of them where I'm pretty sure we're not taking much risk. And carbon, I don't think we take much risk by saying it's very likely to be carbon-based. There's a very simple answer for that. The universe is full of carbon. So why would you use very exotic material when you have so many carbon, and the chemistry of carbon is so fantastic, it's so easy to play with water, and there's water everywhere, that you would expect other kind of life. So I'm pretty sure carbon play an essential role into life. No, there is plenty of other elements that you can challenge. The fact that we have only a single example of life on Earth, I think this is certainly a valid point to imagine that life may not be exactly the same. But the carbon, I'm pretty sure, whether the amino acid of kind of a standard starting ground, possibly, but then there's still a long way to go. Even if you accept the carbon and amino acid, there's still a long way to go to get something alive. And I'm not that sure that we need exactly the same chemistry, the same proteins to produce the DNA structure, the same nucleotide. You can maybe produce other kind of nucleotide and proteins to make it work with a kind of similar encoding. You need some encoding, but maybe you may have a different mechanism to do that. So I will rather bet with another kind of complex chemistry, but on the very basic element, the one from the carbon, I'm pretty sure life is carbon-based everywhere because there's so many carbon everywhere.
Another question here that is more general, and one that I'm sure you often get asked, but it's obviously from a young scientist, from Rachel So in School of Physical Mathematical Sciences, which is, any advice for an aspiring astrophysicist or physicist in general?
Oh, I'm always a little bit scared, but when people ask me advice, and usually I think my best advice is always follow what you like, follow your passions, and whatever it is. I mean, if you get attracted to science because you read a book or you went to a movie or you decided to study something related to astrophysics, that's fantastic. I think that's it. It doesn't mean that you may continue and make a living with astrophysics. You can maybe do something different. I think the scientific attitudes, the beauty, and the idea that we're going to express our natural curiosity, it's something we all have. So I'm pretty sure that to some level we all have. I get the feeling that when we grow up, we tend to lose it a little bit. Not everybody, I think as one of them, that I certainly have not lost anything of my curiosity that I have had when I was younger, because I still believe that I need to understand, I need to learn, and it's kind of the need for drinking water. I'm always thirsty, and always want to learn more, and my advice is just try to do what you really like, and if you're very curious, just go for it. And if you got advice that you should do something more practical, and just don't listen.
Okay, thank you.
I will get into trouble.
We have a question from someone at the microphone, I think.
Hi, my name is Alan Duanyhe. I'm from Huazhong International School, and I want to ask one question. Dr. Didier, you earned your Nobel Prize in physics for the discovery of the first known extrasolar planet, and I'm very grateful to see you here today. And
Thank you.
I want to ask you a question that is less technical, because although I'm a very physics enthusiast, but I want to ask you a less technical question. What is your feeling as a scientific pioneer? What's your feeling at the moment that you know that there are other planets outside our solar system, what's your feeling as the pioneer in the scientific field? Thank you.
Well, what the feeling of this? Well, a lot of people were expecting it. So, I mean, for most of the scientific community, the fact that we found planet was not a complete surprise because it was a long expectations and the idea that they will, I mean, you realize when you form a star, there is something left over, and the planet's a very natural production. So it was not a shock that we found the planet. What was a shock here is we found a planet like nobody had imagined it would exist. And that planet created a cascade of events that has opened a complete new territory, telling us that, well, maybe the solar system is not exactly a kind of standard situation. So I really feel, in a way, I'm part of this long, when you're a scientist, you're part of this long-term, historical perspective, because you know that you've done what you've done because some other people have done something before. And you're using what they have done, and these people and so on, you can go back and essentially go back to the beginning of science, whatever you set it up, Galileo or even before, whatever. So you really build this up. So I feel that I did my job as a scientist, and I'm very excited about the idea that people will be using this because they will be pushing it and doing much better. And in a way, this is how I feel really. So it's a way the job done as a scientist. Every scientist is bringing something. I get a bit lucky because some people are bringing a small stone. I brought a big stone, but it's just one stone amongst many, and my stone would have no value without all the work being done before. So that's my perceptions about this, and I'm glad that it helped us to better understand where we sit. And if it can have some kind of value for the society, trying to address the question, so maybe how rare is our system, how fragile is our planet, well, it's even better. But I don't know how far people will learn, or how far people are learning from the result of science. And we see the controversy sometimes, some obvious fact, which is pretty obvious, like global warming, how much years it took, and it still takes right now from people to be skeptical about the reality. So that sometimes it's not so easy to see what is the impact, the general impact on the society. But you don't control that. You do something, you just see some kind of natural law, and you just explain, and this is already a high value, and what the society is going to do that, we'll see. I may not see it.
Thank you so much.
Thank you. I'm not sure how much time we have. If someone could let me know, that would be helpful. Oh, we don't have time. We're told we don't have time.
Sorry, I spoke too long.
If we don't have time, I'm going to... Yes.
I just want to ask, do you think it's possible for our great-grandchildren to live in another planet?
Oh, okay, living in other planet. Well, okay. I wouldn't bet too much on that for a couple of reasons. Well, first, I think traveling into space is very dangerous. And it's even more dangerous than you think it's dangerous. We're not designed for that. It's something we're not designed, and really Earth is really protecting us a lot into this. So the other reason is I think we are, as a biological entity, we are the product of an evolution which is connected to the Earth conditions. So anything you do outside of Earth, it's impossible it's not a biological entity. So maybe we are going to develop a new human, the post-human, there are people interested about that topics, and this post-human may be able to live on Mars, but us as we are, certainly not our grandchildren, will not be able to do that. We may have to design a new kind of human to do that, because I don't see how we can be alive in such a deadly places. And people that wants to go to Mars, I invite them first to go to the South Pole. 10 years. And South Pole, it's what we call, it's easy. It's kind of vacation compared to Mars. So there's something that we all have seen, the Martian story. And I think this Martian story this is good, sci-fi is good, but it gave a very bad perception. It looks that Mars is okay and you can go there. No, it's not okay. You die on Mars. We're not designed for Mars. So taking care of our planet, that's what I would do, and I would take care a lot of our planet, and I will keep sending probes and looking at things, but I would not try to design a program when you trash our planet or go somewhere else. It's not a good investment, Alice, to do that.
So for those of you in the audience, that question came from Alice Hung, who from Pioneer Ventures, for whom we're grateful for your support for this event. Also to the Institute of Advanced Studies and the College of Science, but most grateful, of course, to you, Didier.
It's my pleasure.
For your time and your words and the thoughts that it's generated. So thank you very much.
Thank you. Thank you very much.
I would like to request Prof. Queloz and Prof. Simon to remain on stage, and I would also like to invite Prof. Subra Suresh once again on stage to present the memento to Prof. Queloz. Lecture, I would like to thank you all for joining us today. Now, I would like to invite the president, the speakers, and the sponsors to please take their leave first. Lastly, we request the audience to fill in the feedback form by scanning the QR code on the screen. Also, for students who need the attendance endorsement, please indicate it in the form. Thank you and have a great evening ahead.